Okay, here's an interesting problem, motion problem, and it involves a situation where we've got two moving vehicles. One's at a constant speed, the other one's accelerating, and we're going to look at when one catches up to the other. That's the crux of the problem. So, if we're identifying the important information, we have speeding motorcycle travels past stationary police car, being the initial speed of the police car is 0. And then the motorcycle is travelling at this speed, 35 meters per second. This is a constant speed, so the motorcycle is not actually accelerating. Okay. Now the police car starts accelerating immediately at 4 meters per second and keeps accelerating. So you've got two types of information there. We've got information pertaining to the police car. So the fact that it's stationary, that's the police car information. And then you've got acceleration there pertaining to the police car. But then you've got information here pertaining to just the speeding car. So we've got to distinguish between the two and separate them. Okay, so let's look at the situation now. Let me try and depict it. Alright, so here's this little dot represents the police car. So here comes the speeding car, the speeding motorcycle. Now, where is it? Nope, didn't work. Alright, so as the car goes past, then at the same time the police car is speeding up and then trying to get there as well. And there's going to be a point where they will meet. Okay, this is a point where they've covered the same amount of displacement from some starting point, and the starting point is going to occur here at t equals 0. Okay, this is like the starting point of when we're measuring time, when acceleration of the police car occurs. Okay, so then from that we're going to have this endpoint here being the same displacement that's occurred. Okay, and so when we're thinking about, well, what is the time that the police car overtakes the bike? This is when the two cars have the same displacement. So this is the first thing we think about. So let's identify what is displacement of each vehicle. So let's use SP. SP is going to be a displacement of police car, and because it's accelerating, we're going to use this rule, ut plus half at squared, and SC is the displacement of the car. That's travelling at constant velocity, no acceleration, so it's just velocity times time. Now, when they catch up to each other, we will have these displacements equal to each other, like that. Okay, when the police car catches up to the bike. So we substitute in our parts. Okay, now just keep in mind that we've got two separate pieces of information. One pertaining to the police car, that's the velocity to the police car. Sorry, that one is velocity of the bike. Well, this one here is velocity of the initial velocity of the police car, which is going to be 0. And that's your acceleration of the police car, and we're told that that is equal to 4. Okay, whereas the velocity of the bike that's traveling is 35. Alright, now let's think about as we substitute our values in, and we try and transpose, bring all our t's to one side, and we're going to solve for t. We end up with two possible solutions. and they are, well, either t is equal to 0, we'll solve our equation, or t is equal to 35 on 2. Okay, now t is equal to 0 is at the start here. This is the point where the displacements are the same. It's 0 displacement. Or we have at the other end over here, this point at the end is some displacement down the road when they are matched as well. Okay, that happens at 35 over 2 seconds. So having found the time, then we go ahead and we can take this time and work out, well, what is the displacement that's been achieved for that time. Okay, using a rule for the displacement of the speeding bike, 35 meters per second times the time of travel gives us something like 612 meters of displacement. So after 612 meters, the copper has caught the bike and he's probably going to end up losing it, be pounded. Very good.